Myself, I'm Keshan from CSC Section B. My topic is on skew-symmetric matrix. Definition of matrix. Matrix in mathematics is defined as an array of numbers arranged in a rectangular fashion and divided between rows and columns. It contains all the numbers arranged in square brackets. The operation of matrices is a very important topic in the mathematics for the board exams as well as the engineering entrance exams. Definition of skew-symmetric matrix. A skew-symmetric matrix is a square matrix that is equal to the negative of its transpose matrix. It is important to know that the method to find the transpose of matrix in order to understand a skew-symmetric matrix better. Here we have considered a matrix A. The basic formula representing a skew-symmetric matrix is as follows: B equals to minus B transpose. A square matrix B, which of size n into n is considered to be a skew-symmetric matrix if and only if B transpose equals to minus B. That is the transposed form of a skew-symmetric matrix or antisymmetric matrix that is equal to the negative of that matrix. This can be represented as if B equals to Vij n into n, Vij n into n is the skew-symmetric matrix, then Vij equals to minus Vji for all I and j are 1 less than or equals to I less than or equals to n and 1 less than or equals to j less than or equals to n. Here n is any natural number. If we put I equals to j, then Vii equals to 0 for all I. This means that all elements that are present diagonally in skew-symmetric matrix are 0. Properties of skew-symmetric matrix. The two important conditions for a matrix to be skew-symmetric are that it should be a square matrix. Example, the number of rows and columns should be equal, and secondly, the given matrix should be equal to the negative of its transpose. Here are some of the important properties of a skew-symmetric matrix. When two skew-symmetric matrices are added, then the resultant matrix will always be a skew-symmetric matrix. Consider two skew-symmetric matrix A and B such that A transpose equals to minus A and B transpose equals to minus B. Then we have A plus B whole transpose equals to minus of A plus B. The trace of a skew-symmetric matrix equals 0. Example, the sum of all elements in the main diagonal is also equal to 0. The real eigenvalue of a real skew-symmetric matrix A, lambda equals to 0. That means the non-zero eigenvalues of a skew-symmetric matrix are non-real. The two important conditions for a matrix to be skew-symmetric are that it should be a square matrix. Example, the number of rows and columns should be equal, and secondly, the given matrix should be equal to the negative of its transpose. Here are some of the important properties of a skew-symmetric matrix. When two skew-symmetric matrices are added, then the resultant matrix will always be a skew-symmetric matrix. Consider two skew-symmetric matrices A and B, so that A transpose equals to minus and B transpose equals to minus B. Then we have A plus B whole transpose equals to minus of A plus B. The trace of a skew-symmetric matrix equals 0. Example, the sum of all the elements in the main diagonal is also equals to 0. The real eigenvalue of a real skew-symmetric matrix A, lambda equals to 0. That means the non-zero eigenvalues of a skew-symmetric matrix are non-real. Addition and difference of two symmetric matrices results in a symmetric matrix. If A and B are symmetric matrices and they follow the commutative property, example AB equals to BA, then the product of A B is symmetric. If matrix A is a symmetric, then A power n is also symmetric, where n is an integer. If A is a symmetric matrix, then A inverse is also symmetric. Theorems related to the skew-symmetric matrix. There are two important theorems related to skew-symmetric matrices in this section. Let's learn about these theorems along with their proofs. Theorem 1, for any square matrix A with real number elements, A plus A transpose is a symmetric matrix and A minus A transpose is a skew-symmetric matrix. Proof. Let P equals to A plus A transpose. Transpose of P can be given as P transpose equals to A plus A transpose whole transpose equals to A transpose plus A transpose whole transpose equals to A transpose plus A equals to A plus A transpose equals to P. A plus A transpose is a skew-symmetric matrix. Next, we let P equals to A minus A transpose. Q transpose equals to A plus minus A whole transpose equals to minus Q. A minus A transpose is a skew-symmetric matrix. Theorem 2. Any square matrix A can be expressed as the sum of a symmetric matrix S and a symmetric matrix V such that A equals to 1 by 2 into A plus A transpose equals to 1 by 2 into A minus A transpose. Here A transpose is the transpose of a square matrix A. If A plus A transpose is a symmetric matrix, then A 1 by 2 into A plus A transpose is a symmetric matrix. If A minus A transpose is a skew-symmetric matrix and 1 by 2 into A minus A transpose is also a skew-symmetric matrix. Thus, any square matrix can be expressed as the sum of a skew-symmetric matrix and symmetric matrix. Determinant of a skew-symmetric matrix. If A is a skew-symmetric matrix which is also a square matrix, then the determinant of A should satisfy the below condition. That A transpose equals to det of minus A equals to minus 1 whole to the power of n det of A. The inverse of skew-symmetric matrix does not exist because the determinant of it having odd order is 0 and hence it is singular. If A is a skew-symmetric matrix which is also a square matrix, then the determinant of A should satisfy the below condition. Det A transpose equals to det of minus A equals to minus 1 whole to the power of n det A. The inverse of a skew-symmetric matrix does not exist because the determinant of it having odd order is 0 and hence it is singular. Eigenvalue of a skew-symmetric matrix. The eigenvalue of a skew-symmetric matrix are either 0 or imaginary values. The real eigenvalue of a real skew-symmetric matrix A lambda equals 0. That means the non-zero eigenvalues of a skew-symmetric matrix are non-real. Proof. Let A be a square matrix and lambda be an eigenvalue of A and X be an eigenvector corresponding to the eigenvalue lambda. X equals to lambda X, multiplying both sides by lambda bar X bar whole transpose. X bar is conjugate of eigenvector X. We got X bar whole transpose Ax equals to lambda X bar transpose X equals to lambda into X whole square. Now note that the term Ax is the dot inner product of X and Ax. Since the dot product to commutative, we have X bar transpose X equals to Ax transpose X equals to X transpose A transpose X. Since A is skew-symmetric, we have A transpose equals to minus A. Substituting this into the above equation, we get, thus we have minus X transpose Ax bar equals to minus X transpose equals to minus X whole square. If A is real skew-symmetric matrix, then its eigenvalue will be equals to 0. Alternately, we can say non-zero eigenvalues of A are non-real. Every square matrix can be expressed in the form of a sum of symmetric and skew-symmetric matrix uniquely. Trace of skew-symmetric matrices. The trace of a matrix is defined as the sum of all its diagonal elements as discussed under the properties of a skew-symmetric matrix. Then diagonal elements of a skew-symmetric matrix are 0. Therefore, the trace of a symmetric matrix are always equals to 0. Eigenvalue of skew-symmetric matrix. The eigenvalue of a skew-symmetric matrix are either 0 or imaginary value. The real eigenvalue of a real skew-symmetric matrix A lambda equals 0. That means the non-zero eigenvalues of a skew-symmetric matrix are non-real. Proof. Let A be a square matrix and lambda be an eigenvalue of A and X be an eigenvector corresponding to the eigenvalue lambda. X equals to lambda X, multiplying both sides by lambda bar X is conjugate of eigenvector X, we get X square. Note that the term X bar is the dot inner product, and since the dot product is commutative, we have, since A is a skew-symmetric matrix, we have A transpose equals to minus A. Substituting this into the above equation, we get, thus we have minus X transpose Ax equals to minus X transpose. If A is a real skew-symmetric matrix, then its eigenvalue will be equal to 0. Alternately, we can say non-zero eigenvalues of A are non-real. Every square matrix can be expressed in the form of a sum of a symmetric and a skew-symmetric matrix uniquely. The trace of matrix is defined as the sum of all its diagonal elements as discussed under the properties of a skew-symmetric matrix. The diagonal elements of a skew-symmetric matrix are 0. Therefore, the trace of a skew-symmetric matrix always equals to 0. Important notes on skew symmetry matrix. Here is a list of a few points that should be remembered while studying skew symmetry matrix. A matrix for which the transposed form is equals to the negative of the original matrix is called a skew symmetry matrix. Any matrix can be expressed as a sum of skew symmetric and symmetric matrix. For a square matrix A equals to 1 by 2 into A plus A transpose plus 1 by 2 into A minus A transpose. If the order of a skew symmetry matrix is ordered, then its determinant is equals to 0. Theorem. Any square matrix A can be expressed as the sum of a symmetry matrix S and a skew symmetry matrix B, such that A equals to 1 by 2 into A plus A transpose plus 1 by 2 into A minus A transpose. Here A transpose is the transpose of a square matrix A. If A plus A transpose is a symmetric matrix, then 1 by 2 into A plus A transpose is also a symmetric matrix. If A minus A transpose is a skew symmetric matrix, then 1 by 2 into A minus A transpose is a skew symmetric matrix. Thus, any square matrix can be expressed as the sum of a skew symmetric matrix and the symmetric matrix. If A is a skew symmetric matrix, which is also a square matrix, then the determinant of A should satisfy the below condition. Det A transpose equals to det of A minus A equals to minus 1 all to the power of n det of A. The inverse of skew symmetric matrix does not exist because the determinant of it having odd order is 0 and hence it is singular. If A is a real skew symmetric matrix, then it here a list of a few points that should be remembered while studying skew symmetric matrix. A symmetric for which the transposed form is equals to the negative of the original matrix is called a skew symmetric matrix. Any matrix can be expressed as a sum of symmetric and the stereometric. For a square matrix, A equals to 1 by 2 A plus A transpose plus 1 by 2 A minus A transpose. If the order of a skew symmetric matrix is odd, then its determinant is equals to 0. And thank you.